In this video, we are going to discuss the stoichiometric point defects in solids. Irregularities in the arrangement of constituent particles of solid crystal are called crystal defects. What is the meaning of crystal defect? Crystal defect means irregularities in the arrangement of constituent particles like ions or molecules, atoms in the solid crystal. It is called as crystal defect. And in this actually video we are going to focus on the point defects or atomic imperfections. The crystal defect that occurring due to imperfections of lattice sites or points are called point defects. Actually, you know that at the time of formation of crystal there is a specific arrangement of constant particles, and lattice points, these are the positions occupied by various atoms, ions or molecules in the crystal, and sometimes these lattice points in the crystal they are missing, and because of this crystal becomes defective. This causes the point defect. There are three types of point defect: stoichiometric point defect, non-stoichiometric point defect, and impurity defect. So what do you mean by stoichiometric point defects? The imperfections in the crystal are such that the ratio of cations and anions remains the same as represented by molecular formula, say for example AB, are called stoichiometric defects. As an example, you consider the sodium chloride. In sodium chloride, Na plus and Cl minus, in between these ions there is a ionic bond or electrostatic force of attraction. Or in such a solid or sodium chloride, it is a AB type of solid, AB. Okay, and in such a crystal, if there is a imperfection in the crystal due to missing cations and anions or dislocation of cations, then the molecular formula or stoichiometry of the resulting crystal will not be disturbed. It will be the actual number of cations and number of anions in the crystal that will remain the same. Such a crystal defect, it is called a stoichiometric point defect. So imperfections in the crystal are such that the ratio of cations and anions remains the same as represented by molecular formula are called stoichiometric defect. So before occurring defect and after defect, the ratio of cation is to anion will not be disturbed. It will be same in this type of defect, that is in stoichiometric point defect. And most common stoichiometric point defects are Schottky defect and Frankel defect. First of all, Schottky defect. If in an ionic crystal of the type A plus B minus, equal number of cations and anions are missing from their lattice sites so that the electrical neutrality is maintained, it is called as Schottky defect. For example, this is the crystal. There is a arrangement of cations and anions like this. This is cation, anion. So alternately cations and anions are arranged. Suppose by some means one cation and one anion are missing from their original sites like this. So here there is a cation vacancy and here there is a anion vacancy. In Schottky defect, the presence of Schottky defect in the crystal decreases the density of crystal, and here there is a loss of equal number of cations and anions from their original positions. Why density of crystal decreases? Because cations and anions, they are not living in the crystal. The missing cations and anions, these are not living in the crystal lattice, and therefore its density decreases. Again, equal number of cations and anions are missing, and therefore stoichiometry is maintained, and therefore Schottky defect is a stoichiometric point defect. So this defect occur in ionic crystal having high coordination number, and cations and anions have almost same size. Normally cations are smaller than anions, but in some crystals cations are nearly having equal size as that of anions, and this Schottky defect is observed in such a crystals where cations and anions have almost equal size. Example: sodium chloride, potassium chloride, cesium chloride, potassium bromide, beryllium oxide, titanium monochloride. These are the examples of Schottky defects. Now next is Frankel defect. In this type of defect, smaller cations are missing from their regular lattice points or lattice sites and occupy the interstitial position. This is the lattice. Here cations and anions arranged alternately, but here in this type of solid or in this type of defect, normally cations are having too small size as compared to anions. And consider this cation after defect, so this cation gets dislocated. So from original position it is dislocated and it occupies the interstitial position, and there is a formation of cation vacancy. And because of this Frankel defect, there is no change in density of crystal, because the dislocated cation exists within the crystal itself and density will remain the same. So this defect occurs in ionic crystal having low coordination number and cations are smaller than anions. Low coordination number means the radius ratio is less or too low. So when radius ratio, that is radius of cation is to radius of anion, this radius ratio low means cations are too smaller than anions. Okay, as cations are occupying interstitial positions, the cations must be smaller, and therefore this Frankel defect occurs in ionic crystals having low coordination number and cations are smaller than anions. Here mass and density of the crystal remains the same, there is no change, and electrical neutrality is maintained, not only in Frankel defect but also in Schottky defect as well. The electrical neutrality, it is maintained, because equal number of cations and anions are missing in Schottky defect, whereas the dislocated cations exist within the crystal itself in case of Frankel defect, and therefore there is no any imbalance in the charges, positive and negative charges, and therefore electrical neutrality is maintained. And these are the examples of Frankel defect: silver chloride, silver bromide, silver iodide, zinc sulfide, potassium bromide, calcium fluoride. These are the examples of Frankel defect. Here cations are too smaller than the anions. Now what are the consequences of Schottky and Frankel defect? First important consequence is, due to Schottky or Frankel defect, the crystal is able to conduct electricity to a small extent by an ionic mechanism, as vacancies are created. Sometimes suppose there is a vacancy of cation, it acts as a hole, and because of hole transfer conduction takes place. So here, due to Schottky or Frankel defect, crystal is able to conduct electricity. This is the most important point. In Frankel defect, similar charges are closer, hence this increases dielectric constant of the crystal. Actually, in Frankel defect, cation is dislocated, and after dislocation it comes closer to other cation, and result of this is there is an increase in dielectric constant, because similar charges when come closer, then dielectric constant increases. So especially for Frankel defect or due to Frankel defect, dielectric constant of the crystal increases. The presence of vacancies in the crystal due to Frankel defect decreases its density. Even in Schottky defect also, greater the number of vacancies, actually this is applicable to Schottky defect, the presence of vacancies in the crystal decreases its density. So density of crystal in which there is a Schottky defect, it is less than the crystal where defect is not there. and if number of vacancies are more, then it may lead to partial collapse of the crystal lattice. Greater the number of vacancies, lesser is the stability of crystal. The crystal may collapse after more number of vacancies due to Schottky defect. And the last point is distinction between Schottky and Frankel defect. Already we discussed some points, just we are having comparison between Schottky and Frankel defect. In Schottky defect, equal number of cations and anions are missing from their original position, whereas in case of Frankel defect, cations occupy interstitial position. Actually they are not going away from the crystal, just they are dislocated, and their cations occupy interstitial position. Okay, this is the most important difference. Another difference is Schottky defect decreases the density of crystal, because cations and anions, they are going away from the crystal. The density of crystal having Schottky defect is less as compared to the crystal where defect is not there. In Frankel defect, there is no change in density of crystal, because cation present within the dislocated cation present within the crystal itself, and therefore density remains the same, no change. Schottky defect observed in crystal with high coordination number or radius ratio nearly equal to 1, because here for Schottky defect, cations and anions, they must have equal size, and therefore this defect is observed in crystal with high coordination number, or size of cation is nearly equal to size of anion, or radius ratio is nearly equal to 1. Whereas Frankel defect is observed in a crystal with low coordination number, especially the crystal with smaller cation, two smaller cation as compared to anion. In case of Schottky defect, crystal with equal size of cation and anions show the Schottky defect, that is radius ratio nearly equal to 1. For Frankel defect, crystal with smaller cations than anions or radius ratio is less than 1. So such a type of crystal shows the Frankel defect. Examples of Schottky defects are sodium chloride, potassium chloride, cesium chloride, potassium bromide, beryllium oxide, titanium monochloride. So all these are AB type of ionic compounds. Equal number of cations and anions are there, and cations and anions have nearly same size or equal size. Whereas examples of Frankel defects are silver chloride, silver bromide, silver iodide, zinc sulfide, potassium bromide, calcium fluoride. These are the examples of Frankel defect. So in this way, in this video, we discussed about the stoichiometric point defects, and actually this discussion was restricted to the Schottky defect and Frankel defect. And in short, point defect means the defect arises due to dislocation or missing of cations and anions or lattice points. This is called as point defect. And in Schottky defect, equal number of cations and anions missing, whereas in Frankel defect there is a dislocation of cation from its original position and it occupies the interstitial site. Okay, thank you.